Hello everyone. I'm really sorry for taking class at this hour. Of course, no one needs to join. I'm recording this, so I was here on Monday. I left it here. Um, so I'll continue from this point. Uh, so we were discussing about the relation about the work done and the strain energy, and uh, as discussed at the very end of Monday's class, I'll first state uh, the version of this corresponding to the normal stresses and the shear stresses, and then go on to strain energy for various types of loading, which will help us to solve problems. So, first of all, due to uh, normal stresses. So, we wish to uh, relate the work done with the strain energy, but for that we are going to consider a an infinitesimal element, a small cuboidal element having infinitesimal dimensions like this. We have dx here and dy here. So this vertical line is dy, and this line into the plane of the screen is dz. And we are going to just consider uh, the strain energy associated with sigma xx. Okay, so we have the sigma xx here. So earlier we had uh, expressed the work done as half of P times delta. So half of P is like the average force when P is applied in such a fashion that the force increases from a value of 0 to P. In a similar fashion, we may understand this thing, that the force associated with sigma xx will be simply sigma xx times dy times dz, and that force is also going to be increased from a value of 0 to the entire value given by this sigma xx times dy times dz. So let me write down the expression for the strain energy, and this time, because we are considering an infinitesimal volume, we are also going to consider correspondingly an infinitesimal du. Okay, and this du, mind you, is associated with the work done due to this sigma xx. So the expression for the force is sigma xx times dy times dz, that multiplied by half gives this as the average force, and that multiplied with epsilon xx times dx, that is corresponding to this delta. So delta is the change in the length, epsilon xx times dx, this dx is like the length, the undeformed length, and that multiplied with the epsilon xx, the strain along that direction, that gives me the change in the length of this element in this in the same direction that sigma xx is being applied. So this part is the force and this part is the displacement. Now you can easily see that this is simply half of sigma xx times epsilon xx, then dx, dy and dz. So dx, dy, dz is nothing but the infinitesimal volume dv that we can directly write, which means that we can slightly rearrange this thing. So du, you take the dv to the denominator on the left hand side, du dv becomes half of sigma xx epsilon xx. Now this is this can be interpreted as the strain energy per unit volume. Okay, this is the strain energy per unit volume, and this has a special name. We refer to this as the strain energy density. This is an extremely important thing to note. The strain energy density U naught, and that is given by half of sigma xx epsilon xx, when of course we are concerned with the strain energy change associated with just this uniaxial stress. So this is the due to normal stress. Let us now move on to the strain energy associated or due to the shear stress. So due to shear stress, so again we are going to consider a a little element, an infinitesimal element, and we are going to consider it in this fashion. So this is the element, and in the deformed configuration it looks like this. So very a picture which is very familiar to us. Now you understand that this direction here, just like before, it is x, and this direction here it is y. And although I did not draw it for convenience, the direction out of the plane of the screen is z. So although this looks like a square or a rectangle, we are actually considering a proper cuboid. Now the shear stress of concern, we are going to consider it the tau xy. So tau xy will be like this, and we wish to determine the strain energy change associated with that tau xy. So this tau xy can also be viewed as a force by multiplying with the appropriate area. You understand that this edge has the length dx, and because that tau xy is acting on the top face of this cuboid, so the area of that top face is given by dx into dz. Okay, so du is equal to half of tau xy dx into dz. So this is the force, and just like before we have to multiply this with a certain displacement, and that displacement will be given by the shear strain gamma xy. That gamma xy, you please note, is this angle. This is gamma xy. So the distance over which the work associated or the force associated with this tau xy is doing the work, that is this particular distance. Okay, this distance from here to here, which is where the displacement is occurring, and that distance is approximately given by gamma xy times this thing. Okay, so actually it is this edge times the tan of gamma xy, but for small angles tan of gamma xy is almost equal to gamma xy. That is why gamma xy times the dy will give us the displacement. So we can rewrite this as half of tau xy gamma xy dx dy dz, and this thing is again the volume. So half of tau xy gamma xy dv, and now it is something very familiar to us from the previous page. We have this thing. So the strain energy density associated with the shear stress will have this expression. Please note that in the previous page, when we are talking about the normal stress, and on this page when we are talking about the shear stress, we are not confining ourselves to any particular nature of loading. Okay, we are just talking about normal stress and shear stress in a very generic fashion. So in different circumstances, wherever normal stresses may appear, for example, as you have seen many a time through your tutorial sheets and assignments and tests, that in the especially considering the problems involving combined loading, that normal stress may be arising due to normal forces or axial forces. Normal stress may also appear due to bending moment. Okay. Similarly, tau xy may be directly due to the transverse shear stress. It may also be due to torsion. Okay. So for these different types of loadings, depending on what the situation is, it will be our job to write appropriately the expressions for sigma x xx or sigma yy or sigma zz, whatever it is, and the tau xy, tau yz, tau zx, whatever the situation demands. So with this knowledge regarding the strain energy density associated with the normal stresses and the shear stresses, we are now in a position to specialize to specific cases for writing the strain energy density for various types of loading. Okay. So strain energy for various types of loading. Please note I am writing the strain energy, not the strain energy density. Okay. So strain energy for various types of loading. Please note this very carefully, because these are the kinds of expressions which we'll have to repeatedly actually utilize in our problem solutions. Okay, so first of all, strain energy due to axial load. So let's write it like this, that delta U, the total change in strain energy, that you can think of like this, that this is basically integration of du. Okay, and so from some u1 to u2, or you can equivalently think of it like du dv times dv, and you know that du dv is nothing but the strain energy density. So because we have general expressions for the strain energy density associated with both the normal stress and the shear stresses, we can write this delta U using the expression for strain energy density basically. Okay, so let's see how we can do this for axial loading. Now, we've already seen that U naught is half of sigma xx epsilon xx dv. Now, if you are considering a uniaxial stress kind of situation, okay, and you apply the Hooke's law, then epsilon xx is equal to 1 by E sigma xx minus nu sigma yy plus sigma zz. And for such a uniaxial case, uniaxial stress case, you have, by that very word uniaxial, it means stress only along one direction. So sigma yy is equal to 0, sigma zz is equal to 0, and this is simply sigma xx divided by E. Okay, like a very simple Hooke's law. So this thing becomes half of, so you substitute epsilon xx is equal to sigma xx by E. This thing becomes sigma sigma xx square by twice E dv. Okay. Now, because we are considering the sigma xx arising due to our axial load, let's say the axial force is capital N, then sigma xx, if you view it like the average normal stress, then it simply becomes N by A. Okay, where A is the cross-sectional area of concern, and if you just substitute this expression here, it becomes a very neat and clean expression, and this is something which we actually use while solving problems. Okay, so this is just the beginning of uh, the first part, or just one part of our recipe for solving problems. So this is simply due to axial load. Similarly, we can consider the strain energy due to bending moment. Let's do that. Uh, we'll follow exactly the same kind of template to determine the expression for delta U. Please note that we can slightly simplify this thing. Okay, how? Achha, by the way, I made a mistake here. This thing, because this is sigma xx square, so when I substitute n by a, this should be actually twice a square e. Okay, and this dv, if you are considering a case of a prismatic beam or a prismatic shaft, then the area all along the length will be equal. Okay, and even if you don't consider prismatic case, then also you can definitely write it like this, that the infinitesimal volume dv can be written as the cross-sectional area over the little distance dx. And now you can cancel this a with the with one of the a's in the denominator, so that the final expression becomes n squared by twice ae dx. Mind you that when you are actually doing a problem, this x will vary over a certain distance. Okay, maybe if you have a beam of length L, then this x will vary from 0 to L. Okay, so please note that I have been a little bit sloppy with the way that I am sometimes writing the limits and sometimes I'm not writing the limits. So at least I can put it here because I do have a dx here. But here you understand that all these integrations where I have not put any limits, they are over the entire volume of the beam or the shaft. Okay. Now coming to the expression of the bending moment, coming back to it. So we have, again just like before, half of sigma xx epsilon xx dv, and this thing is again using the Hooke's law, sigma xx square by twice e dv. Now sigma xx is my by I. Okay, minus my by I doesn't matter because you have the square here, so you will end up with m square y square divided by twice e I square. Okay, now of course you have this dv. Now what we'll do is we will just like before, we will decompose this dv as dA, or we'll just write this dv as a dx. Okay, now you see this thing, this one integration that I have written, it is still over the entire volume. And maybe I think it's better idea if I just transfer this entire thing to the next page. I'm running out of space here. Okay, and maybe take this. Okay, so now what I want to do is decompose this single integration over the entire volume into something like this. So the outside integration, so you understand that a volume integration is basically like a triple integral. Okay, so what I'm going to do here is that this 0 to L, so this is like the integration with respect to dx, and if I do that, so this is exactly this is actually what I'm trying to do here. So I have taken out this 0 to L integration, and then I'll be left with this integration which will be over the entire area. Okay, now uh, so I want to write it like this: m square uh, y square by twice e I square uh, okay, so I made a slight stupid mistake. This thing, I want to write this as dA dx, because in this part only I want to write this as, I want to decompose that integration. So this is over the entire area, this is over the length. Okay, so now I'm all right. So uh, what I want to do now is that, you see, uh, this m, it has nothing to do with the area. So over the cross sectional area, the m is a constant. It need not be a constant with respect to x. So what I can do is I can take this m outside this first integration with respect to a. Similarly, this e and I square also, that 2ei square, that also can be taken outside the integration with respect to a. So I have something like this. Okay, now you see, uh, this is over the entire area and this is dx. Okay, so it's something like this. Now you see this integration y square dA, what is this? So uh, this is nothing but the I itself. So what I have now is m square by twice e I square times I, because this entire integration y square dA, that is the I times dx. So I end up with integration 0 to L m square by twice ei dx. So for beam problems, this is extremely important. Okay, I cannot emphasize this enough. Delta U, the total strain energy change associated with a bending moment, will be given by this expression. Remember this. Okay, this is extremely important. It comes time and again in almost every problem, like not almost every problem, in every problem involving a beam, involving a shaft. Okay, so this is for bending moment. uh, Next, for transverse shear, we are going to consider the delta U, the change in strain energy, by considering the other expression, that is the one due to shear. So half of tau xy gamma xy dV. Now again, by the Hooke's law, the uh, gamma xy is nothing but tau xy by g. Please note that if I had written this as epsilon xy, then this would have been equal to tau xy by twice g. But this is gamma xy, and gamma xy is twice of epsilon xy. So there is no need of this 2 factor here. So what I will obtain after substituting the expression for this gamma xy here is tau xy square by twice g. Please note that this 2 is because of this 2. Okay. Now, earlier I had been substituting the expressions for sigma xx. In the axial load case, it was n by a. For the bending moment, it was my by I. For tau xy associated with the transverse shear, I know that the expression is, just by picking up the appropriate formula, it is vq by it. This is exactly what I'm going to substitute here. So this is v square q square twice g I square t square dv. Now this is a rather complicated looking thing, and we are deliberately going to make it a little bit more complicated in the intermediate steps, but ultimately it is going out to be a nice looking expression. So what we are going to do is something like before, where we decompose this dv into an area integration and a length integration. So 0 to L, because you understand that these are the kinds of expressions which we had obtained in the context of beams, so it makes sense to proceed by thinking of in terms of beams. So this is over the area. This is v square q square twice g I square t square dA dx. Now see, over the entire cross section, this v is a constant, twice g is a constant, I square is a constant. So I'll take this out. Okay, take this out over the of this area integration. We'll be left with v square by twice g I square. I will keep the q square and the t square within the dA, because as we consider different areas, the t may change and the q may change, that you know very well. So q square by t square dA, this is one integration, and then outside we have this dx. So this has become more complicated looking compared to this, but we are not done yet. We are going to make it a little bit even more complicated, but there is a reason for this. So you see, earlier we were able to substitute whatever we had obtained with respect to this area integration. If we just take a quick look back at the bending moment in the previous page, we had this expression integration y square dA, but that was simply, we could substitute as the second moment of area. Now we directly don't have a corresponding thing for this particular integration, but we can frame it up, okay, without too much difficulty. What we'll do is we will define something called a form factor for shear. Okay, so it's something like this. So this is the flow. After this step, we do this, define something called a form factor for shear. This is F is equal to, so we are defining it, okay. So it is our choice that we make it like this. See, we have picked up this integration, which is integration q square by t square with respect to this area, and then we have just multiplied this entire thing with a by I square. Now, why you have done something like this? One motivation is that this form factor, we want it to be a non-dimensional quantity. Okay, now if you check for yourself, you'll be able to see that this here is m square, the I by itself is m to the power 4, so this becomes m to the power 8. So m square in the numerator, m to the power 8 in the denominator, this is 1 by m to the power 6. The q is something like y times an area, okay, a distance times an area. So q by itself is has the unit of meter cube, so that squared becomes meter to the power 6, and in the denominator you have simply meter square. Okay, so this thing, this q square by t square, it becomes m to the power 4, and then you also have this integration with respect to a, and that a is m square. So you have m to the power 4 from here and m square from here, so this entire thing becomes m to the power 6. And remember that this was 1 by m to the power 6. So m to the power 6 in the denominator, this entire thing is m to the power 6. So this thing is actually dimensionless. Okay, so it has been defined in such a clever fashion that the entire thing is made dimensionless. Now, and this is an entity which is purely dependent on the geometry. Please note, it has nothing to do with the Young's modulus or the shear modulus or anything. It's a purely geometrical entity. So for various kinds of cross sections, we can obtain very standard values of this f. Okay, so now if we just pick this up and put it back here, then what we are going to obtain is that, you see, this thing is just with a little transposition, it becomes fi square by a. So this entire integration which is here, it becomes form factor times I square divided by a. So therefore, if we go back to this expression for delta u, so our delta u, it becomes, so I'm picking up from here, it becomes 0 to L v square by twice g I square, and then we have f I square by a times dx. This I square cancels with this I square, and we are left with integration 0 to L f, this f form factor written first, times v square by twice g into a dx. Please note that the form that we have obtained for this delta u associated with the transverse shear has the same kind of form that we were obtaining earlier. So let's check. For the bending moment, it was, so the bending moment is the cause, this delta u is the effect, and that is coming as m square by twice ei. Okay, previously for the axial load, we had the n was the cause, the delta u was the effect, and it was coming out as n square divided by twice ae or twice ea, whichever you want, way you want to look at it. So in the denominator you have one cause from the material, one from the geometry. Here also you are obtaining the same kind of thing, that this is the cause v, this is the effect delta u, and in the denominator you have one factor from the material, this is the g shear modulus, and one factor from the geometry a. Okay, and this, mind you, is a perfectly non-dimensional entity. Okay, so for a rectangular cross section, you can check for yourself that for a rectangular cross section, you can check for yourself that f will come out to be 6 by 5. Okay, I will not do this myself. If you have any problem, let me know, we'll take care of it. So please check this yourself. So we have finished axial load, bending moment, transverse shear. Next, torsion. So again, we have to relate the change in the strain energy using the expression involving the shear, because that is what is associated with torsion. So we are going to obtain this half of tau xy times gamma xy dv, and again using the Hooke's law, whereby gamma xy is equal to tau xy by g, we obtain tau xy square by twice g dv. Now what we are going to do is use the expression of the shear stress associated with torsion. I mean, this is the general expression, but please note that when we are talking about torsion, it makes much more sense to be to be talking not for tau xy, rather with the tau z theta. Okay, so you can think of it, I mean, it's better to write like this. Okay, so this is the tau z theta actually. Okay, and let me make the corresponding thing here, that this tau z theta is equal to so this expression for torsion will be Tr by J, where J is the polar moment of inertia. So this is I'll just substitute it here. I'll obtain T square R square by twice G J square. Correspondingly, what I want to do is I want to decompose this dV also into this kind of an expression. So twice pi r dr takes care of the elemental area, and that multiplied with the axial direction element, the dz, that will give me the entire contribution to the volume. So this is 0 to L. So this 0 to L is for the integration with respect to dz, and then we have the 0 to R. That integration is actually with respect to R. Please note that we are we have already done the integration with respect to theta, because you have done this, written this as twice pi. Okay, this is a perfectly axisymmetric situation, so no need to worry for variations along the theta. It's constant along that direction. So it's like this. So please note that along the radial direction there is no change in the t, there is no change in this twice g, there is no change in the j. Okay, so they may as well be taken out of this integration with respect to small r, and we can write this as this thing, and what we'll be left with inside is this twice pi r dr, and this is simply this is so sorry, this is, there's a r square here, there's a r here, so this is r cube. Okay, so this thing becomes 0 to L T square by twice G J square, and then we have twice pi, this is r to the power 4 divided by 4. So all in all, what we'll be left with is pi r to the power 4 divided by 2. Okay, I've just done a little algebra by erasing some stuff. Okay, so this is the thing. Now please note that this pi r to the power 4 by 2, this is nothing but j itself. So that j will cancel with this j square, one of it, and we'll be left with t square by twice gj dz. And this is again in the form which we are familiar with the previous cases. This t is the cause, this is the torsion, this delta u is the effect, and in the denominator you have one factor from the material, the g, and one factor from the geometry, which is the polar moment of inertia. So that's it. So these are the different expressions for the strain energy change associated with the different loadings. So we'll take a little break here. Rather, I will take a little break here.